Discussion about sequences are the precursor to discussion about series. Series are built out of sequences. So let's start with, suppose someone has a starting salary of $30,000 and then they get a $2,000 raise every year. So that's pretty easy to see, your first year, second year, third, fourth, and fifth year. So these are the terms of the sequence that describe their salaries over a 5-year period. This number has a sum of $170,000, which means that's the amount they earned over the course of 5 years. Any sequence can be used to define a series. What you see here is a finite series because it has exactly 5 terms to it, or an exact set number of terms. We can use any sequence, so example, this with these 3 dots, that means it's an infinite sequence. And this sequence defines the infinite series like this, where we're adding each term together. So what we can do is define the sum of the first n terms, just like this, right? So what we do is we take s sub n, meaning n number of terms of the sequence, and we add the first term plus the second plus the third all the way to that nth term, whatever it is. When we add that together, that's how we get this idea of series. We have added together the terms of a sequence. We don't write it in this manner. Usually we use what's called summation notation, using the symbol sigma, which indicates taking a sum. Notation is very important when we're dealing with series. So what we do is we take the sum of some value, some index value I, starting at, typically it's 1, up to a specific number, and whatever that is, a sub I. What that means is we are going to take this and start with my first term plus my second term plus my third term all the way to my nth term, and that's a finite series. We can do the same thing with infinite series. Typically, again, we start at 1, but we go to infinity, and we would add these items up infinitely. What we're going to be doing when we talk about infinite is generating formulas. Pay attention to this letter I. It's the index number. Don't confuse this with I, which represents the square root of -1. These are not the same thing. You also might see K and J used instead of I. Let's start by evaluating the series. We're going to add up, starting with j equals 1 up to j equals 5, this. So let me show you what that looks like. With j equals 1, we've got 1 squared plus 1 plus 1, plus j equals 2, 2 squared plus 2 plus 1. And then when j equals 3, 3 squared plus 3 plus 1. When j is 4, and then when j is 5. So this is 1. 4 plus 2 is 6. 6 plus 1 is 7. 9 plus 3 is 12 plus 1, that's 13. 16 plus 4 is 20, that's 21. 25 plus 5 is 30, so then 31. Hope you guys caught my mistake. 1 plus 1 plus 1 is 3. So I've got 10 plus 13, that's 23. Plus 21 is 44, so I get 75. Our next set of problems tells us to write the terms and then, if it's possible, to actually evaluate the sum. So we'll look at the first one, b sub I, when I is from 1 to 5. So what we're looking for is b sub 1 plus b sub 2 plus b sub 3 plus b sub 4 plus b sub 5. Now, since we don't know what b is, we can't evaluate the sum. But let's take a look at the next one. We're going to start at j equals 1 to 4. And we're going to look at 2x sub j minus 5. Now, we've been told that x sub 1 is 3, x sub 2 is 5, x sub 3 is also 5, and x sub 4 is 9. That can't be right. X sub 3 is actually 7. So when j is 1, we have 2 times x sub 1, which is 3, minus 5. Then we have 2 x sub 2 minus 5. Then we have 2 x sub 3 minus 5. And then we have 2 x sub 4 minus 5. So I get 6 minus 5 is 1, 10 minus 5 is 5, 14 minus 5 is 9, and 18 minus 5 is 13. And the way I think about this is I say 9 plus 1 is 10, that makes 23, and add 8 to 23, and I should get, add 5 to 23, and I get 28. This next problem has a lot going on to it, and this is more like what you are likely to see when you get into calculus classes, finite math classes, and even statistics. So we're looking for a sum. We're only going from 1 to 3, but we need f of x sub k times delta x. So we've been given a lot of information. First of all, f of x is 1 over x. Delta x is 4. So those are simple enough to deal with. So now we're dealing with the x sub k. So there's x sub 1, x sub 2, x sub 3. So what I do is I write all of this out. F of x sub 1 is 1 over 1 times 4. F of x sub 2, well, x sub 2 is 3 times 4. And then f of x sub 3, x sub 3 is 5. We multiply that by 4. So I get 4 plus 4/3 plus 4/5. Now when I'm adding this together, I need a common denominator. My common denominator would be 15. So 4 then becomes 60/15. 4/3 becomes 20/15. And 4/5 becomes 12/15. For a sum of 92/15. This is a little bit difficult to see, so I'm going to explain each one individually. We are told that all of the A things and the B things are different sequences. C is a constant, meaning it's just some number. And then, of course, N would be the number that you end on. So, if you have the summation of 1 to some number of just a constant, then all you have to do is multiply the constant times this top number. If you are taking the summation of some sequence times a constant, then what we can do is pull that constant out, do our summation for our sequence, and then multiply that answer by the constant. When we are taking summation of two different sequences that are being added together, we can do each one individually and then add those two solutions together. Same thing when you're subtracting. You can do each one individually and then subtract them. A couple of rules that we're dealing with. If we've got the summation of just our index, so what we're doing is 1 plus 2 plus 3 plus 4 all the way to our maximum number, we can actually use this formula to calculate that without having to add each number individually. These rules apply if we're dealing with our index value squared and our index value cubed. This is the equation for squared, and this is the equation for cubed. If I expect you to use these, I will give them to you. So let's use our summation properties to find the sum. The first one, we just have a constant, right? So that's like example A. We're taking the summation of a constant. That constant is 12, and we're adding it to itself 50 times. So that's simply, we multiply 50 times 12, which is equal to 600. The next one is a little bit more of a challenge. We've got 3i. So this is going to use two different rules. The first rule that we're going to do is we're going to take this constant and pull it out front. So now we've got this that we can use the formula from the last slide, meaning we're going to take 3 times n, which is 35, times 35 plus 1 over 2. So that becomes 3 times 35 times 36 over 2. 35 times 36 divided by 2 is 630. 630 times 3 is 1,890. The last example is using 3 different rules. The first thing that we notice is that these are being added together, so we're going to start with that. We're going to say, okay, well, I need the sum from I is 1 to 10 of 3i squared plus the sum of I from 1 to 10 of 5. Then I see that I've got this 3, so that can get pulled out. So that becomes 3 times the sum from 1 to 10 of I squared plus the sum from 1 to 10 of 5. When I use that I squared, again, that's one of the ones from the second page I get, or the last slide, I mean, 3 times n, which is 10, times 10 plus 1, times 2 times 10 plus 1, all over 6. And then when I'm just dealing with a constant, that's just like the one that we saw up here. We just multiply. So we multiply 5 times 10, which is 50. So from here, I'm just going to plug all of that into my calculator, but I'm going to be very careful when I'm dealing with parentheses. When I plug this into parentheses, this big section here gives me 1,155 plus 50. When I add those together, I get 1,205. on this last example, we've got another pretty complex summation, so because it's adding and subtracting, I can separate this into 3 separate summations. So the first one, I'm dealing with a cubic. Again, that comes out of that yellow box. And I get n squared, well, n is 5, times 5 plus 1, quantity squared, over 4. Now, this summation that's in pink has another step to it, so I'm just going to move that here because I have to pull the 2 out. With this one, I'm going to say that it's 2 times n, which is 5, times 5 plus 1 over 2. And then the blue one, that's just a constant, so all I have to do is multiply 8 times 5. Now, when I put the one that's in black in my calculator, 25 times 36, and I divide that by 4, I get 225. When I go through the computation on the one that's pink, right, 5 plus 1 is 6. 6 times 5 is 30. 30 divided by 2 is 15. 15 times 2 is 30. And then the blue one is easy. So now I just have to put these numbers into my calculator, which is simple enough, and we get 215 as our solution. Alright, so now I'm going to show you how to use the calculator to do a summation like the one that you saw. This is one that we actually did by hand. So the first thing that you have to do is you have to go to second stat, which is your list, and you need to arrow over to the operations, and then you need to go down to the one that says sequence and hit enter. Now what you're going to do is you're going to put in the equation, the j squared plus j plus 1. So in order to get j, you have to hit alpha, and then j is the comma button, so j squared plus j plus 1. Can you guys see that? I hope so. There we go. Now from here you have to put a comma. And you have to tell it, okay, well I want to use j, so you put j in again, comma. I'm going to go from 1, comma, up to 5, and then you are going to close your parentheses. And you're going to say, okay, when you do this sequence, what I want you to do is store it. So store is way down here, so that's store. And you're going to store it in L1. So for L1, you go second, and the number 1. And your screen should look like this. And after you do that, you hit enter. Now, you can very easily add these numbers, or you can tell the calculator to do it. To tell the calculator, you go back to second stat, and this time we want to do math. And we want the sum, which is number 5. And we want the sum of L1, so again, second, 1, close those parentheses, and hit enter. And we get 75, which is exactly what we did calculating this by hand.